Thanks for joining me again today, guys. I have a pretty interesting example I want to show you for one of my more recent code examples. In this case, I was very surprised to find out that doing a bunch of Monte Carlo searches, I was actually able to find, and looking at lifetimes of satellites, you can actually find geos that decay in less than, 70 years or so. So if you want to learn more about that, as well as how to set up large Monte Carlo lifetime analysis for your satellite, watch till the end. All right, I've already kind of hinted at it, but this is another one of our code examples that is up on our GitHub, and I just want to sort of walk you through that. Frequently, we'll have customers call in all the time, ask all sorts of lifetime questions, and then they want to set up maybe like a Monte Carlo analysis, perturb their satellite, see what happens if I have launch errors, things like that. So what I did is end up writing another Python code example, which will allow you to go through and automate different sort of variations for your satellite, or do a satellite search space, and set up these sort of large-scale trade studies for lifetime analysis. So here is the first example. I just want to walk through how you can run this. This particular example is a Jupyter Notebook, again in Python, and it's called Run Lifetime Analysis. And so the way this works is you're going to open up in Jupyter Notebooks, and then you will run this sort of right here, this config settings. So there's a configuration file that has pretty much all the things you're going to want to vary for your lifetime analysis. It'll save things like where do you want the results to be saved, how do you want to vary it, do you want to do a grid search, a let in hypercube, or perturb your satellite state. Those are the three options I have in there right now, as well as how many number of SDK instances do you want to launch to run this sort of analysis on. You can, if you have the licenses and the number of cores to support it, you can launch as many as you want. You can also have it run HPOP, so you can do a lifetime versus HPOP comparison. A couple other settings, I'm not going to go into them all, but pretty much everything that's going to be related to your satellite state, as well as the drag area, mass area, your satellite properties, and then lifetime configuration options, such what atmosphere model do you want to use, what solar flux file do you want to use, what sigma level, all those sorts of things you can set up and vary in your trade study. So how this works is we have this default configuration right here. We can go and modify those properties, such as change the file name, change what we want to do. We maybe want to do a grid search, play with these options right here. You can change the satellite state. And then I have a couple pre-built examples. In this case, this example, I'm just going to do a very simple grid search. I'm going to vary the values of pretty much the orbit state, the semi-major axis, eccentricity, inclination, argument of perigee, and RAN over these values right here. So these are going to be entered as simple like NumPy arrays, pretty standard Python right here. And in this case, it's just going to vary between a semi-major axis of 6778 to 7178 in steps of 100. And I'm not going to go through all these elements right here, but this is a really quick, a simple grid search. It's going to look through a lot of LEOs, so you can maybe start doing for this type of LEO, what might be my lifetime that I might expect. There's a whole bunch of other configurations. I have a huge spreadsheet of different results I've run to address some of these lifetime questions. But here I just want to walk you through how you run it, and I'll go into some of those results a little bit later on. So we've now set up our trade study. You can save this configuration so you can load it back in later, as well as all the results. All the results are going to be saved to a CSV. So this just saves your configuration right here. And then this actually creates the run. And if you've already run it previously, it'll go through and make sure that it's not going to overwrite anything you already have saved. Otherwise, it will generate these new set of runs for you. So if I scroll down, in this example, it looks like there are 768 different LEOs that I'm going to run. And then in this case, you can see the semi-major axis, the eccentricity, and all those values that we told to be varied are being varied. And then here's a real quick summary of that sort of analysis. You can see that the semi-major axis is being varied. It has a standard deviation, eccentricity, inclination. All these are being varied, and then anything we're not varying really isn't going to have any standard deviation. It will actually go through and calculate the XYZ Cartesian positions for you. So if you wanted to vary in that sort of space, you could. But other things like the coefficient of drag, the CR, all those other values that were not varying, they're not being varied, and you can see that in the standard deviation values over here. And just sort of get high-level summary statistics of your trade study. So when you're ready to actually run this, you're just going to scroll down here to this cell right here, and it will run the trade study for you. I'm just going to go ahead and do that. I've already actually run this result, so the script is smart enough to say, hey, you've already run this. I'm not going to rerun it. But if I go to cells and click run all, it'll run through and say, hey, I actually already have these results saved, so I'm not going to rebuild everything. But if that CSV file didn't exist, or if there were rows in it that were empty, it will start up SDK, it'll launch as many number of instances as you said, and it will run that for you. So that's real quick what I just want to cover with how to run these large, scale trade studies with LifeTime. And now I just want to go into some of the more interesting results. So this is really driven by the common questions that we get from working in support. Things like, what atmosphere density model do I use? What does Gaussian quadrature mean? What value should I put? What about orbits per calc? Or should I turn on this second order ablateness effect? All those sorts of things I have built trade studies to sort of address. And the key summary is, they're up here at the top. I can tell you which atmosphere models tend to give good results, which ones tend to run longer, which ones tend to give different answers than the others, as well as sort of what settings should you use. And that you can read this if you want to learn that sort of information. I'm just going to walk through some of those, as well as a couple other trade studies I happen to do, like comparing the accuracy of HPOP to LifeTime, that sort of general summary. And then as you already sort of saw, there was a little bit of a teaser. I was running this analysis over a whole wide orbit regime, and I was looking and I saw geos that seemed to be coming in like 40 years. And I was like, what is going on? Maybe there's a bug in my code or something. But it turns out I found a pretty interesting physical phenomenon that I'll cover in a little more detail. Okay, so real quick, high level, what are the general LifeTime settings that you might want to run, at least judging from these trade studies? I'm going to scroll down here, and you can see right here, there is a correlations between LifeTime and things like radius of periapsis, semi-major axis, inclination, flux sigma level. So in the LifeTime tool, you can say, +1 sigma, +2 sigma. That will basically increase the effects on the atmosphere puffing out from the sun. In this case, you can see it has a negative effect, but only about -6%, opposed to something like radius of periapsis, which is highly correlated with your orbit lifetime. Pretty much the standard things you might think of that are going to be correlated with your lifetime: radius of periapsis, semi-major axis, flux sigma level. Those are captured, and quantitatively too, not just qualitatively, which is the point. If I scroll down here, and if I want to look at what atmosphere density model should I use, in this case, I think I did a grid search, so it's going to be the same set of LEOs are going to be run, but with different atmosphere models. You can see that for the most part, all these guys are giving 9 to 10 for their average lifetime for these LEOs, except for one right here, the 1976 standard atmosphere. That guy tends to give low results, and the summary statistics are sort of right here. The Harris-Priester tends to always generate longer lifetimes than the other atmosphere models. The circa 1971 and the Yakia 70 lifetime, those tend to be fine, but they just tend to run a lot longer. So really just these four right here are the ones I would maybe recommend steering away from. But the rest of the atmosphere models, they have their own differences, but they tend to give roughly the same answer. And that also kind of confirms what has been done in a previous one of our studies, which is actually one of our white papers on our website. So we got consistent results there. That's great. But these are the atmosphere models I would recommend picking from. Another common question that you'll get asked is, what solar flux file should I use? What flux sigma level should I use? How much does it matter? And I really just want to address that here. In this case, I'm showing the default for the lifetime tool, the solar flux CSSI.dat. That's the default. And you can see what happens for these LEOs. It looks like the lifetime drops by about a year and a half or so. Obviously it depends on, you can look at the exact difference here, but there's about a year and a half difference depending on if you increase the flux sigma level by 1. Again, this is for LEOs. Obviously, it's not going to have a huge effect if you're not in the atmosphere. But this is, you can sort of start to quantify how much of an effect it would have for different flux sigma levels. Here's a sort of a plot just to show that a little bit better. You can see that the lifetime is very heavily correlated with the radius of periapsis. Also in this plot though, this orange line right here is the space weather file. That's the other file that people typically will use. And it's going to agree pretty well with the CSSI file up until these sort of longer lifetimes. And the reason for that, it turns out, is the CSSI file will repeat once it runs out of data, but the space weather file just, I think, holds on to the last value. So it really shouldn't be used if you're doing stuff with lifespans beyond like at about 2043, which is where that file ends. If your orbit goes past that, I wouldn't recommend that space weather file. Instead, I'd stick to that CSSI file. And here's, we can go a little more detail. I'm actually just plotting the solar flux over time. But yeah, that's the big summary for those two. They're going to give pretty similar results. There are some slight differences. During the solar max, the space weather file will predict a slightly larger number of satellites coming in, but they're pretty consistent overall. Some other questions that get asked are, what are the effects of Gaussian quadrature? That's pretty much how often you're going to sample your atmospheric density. And in short, the summary here is, it turns out that a Gaussian quadrature of 2, which is sampling twice per orbit, is almost as good as sampling. In this case, I ran an example of 75 samples, and they give almost the exact same value. So generally speaking, for this value, I would just recommend setting it to 2, because anything with an eccentricity above, I don't know, 0.1 or so, you'll start to see a deviation between a Gaussian quadrature of sampling once per orbit versus twice. But once you start sampling twice, you're not seeing much more of effect. Like if you go to 3, 4, 5, 6, all the way up to 75, you get pretty similar results. So just setting that to 2 is great. And then the only reason you wouldn't want to crank it up to 100, which is the max, is it's just going to make your runtime about 100 times longer if you go from 1 to 100, because that's to sample and do about 100 times as many calculations. It's approximately linear there. So if you set that to 2, you're in most cases golden. If you have some really elliptical orbits, you might want to set to like 4 or 8 or like maybe some multiple of 2. But for the most part, setting at 2 and you should be good to go. Some other types of questions you might get asked are the epoch, when do I launch? How would that affect my orbit lifetime? And here's a real quick summary. If you're launching between the year of 2020 and 2040, I ran a bunch of LEOs with different eccentricity values, and you can just see, roughly how long is your lifetime going to be. And you can see this sort of oscillatory pattern that comes from the solar mins and maxes. And it looks like for a 600 kilometer radius of periapsis orbit, those fluctuations due to the solar flux min and max, when you launch versus like right before a solar max or like right after, it looks like about 4 years and for that particular LEO. But you can go look and investigate this a little more. And then all these sort of plots, if you want to convey results, you can go modify these as well. Another question you might get asked is, how does HPOP compare to the LifeTime tool? Or rather, how does LifeTime tool compare to running HPOP? So if you configure them the same, it turns out that they're pretty accurate. But there is one setting that I would recommend turning off if you're going to try to compare these two. For LifeTime tool in general, I'd recommend turning off. There's a term called the second order ablateness effect. If you uncheck that, sometimes that'll cause the satellite appears to decay a little bit sooner. But with that unchecked, here's the sort of slope right here. A 1 would be a perfect correlation. So the LifeTime tool and HPOP runtime, lifetime predictions are pretty good with that setting turned off. Otherwise, with the LifeTime tool turned on, it tends to sometimes for the longer orbits, it'll predict a little bit shorter lifespan than HPOP. Anyways, if you uncheck that, they match pretty well. And if we start looking at some of these sort of statistics right down here, and I looked at like different errors, like these percent errors, with the LifeTime, with that box unchecked, the percent error is only about 3% for most of these LEOs. Whereas it's 7% with that checkbox on between the LifeTime tool and HPOP, which also sort of quantifies, how accurate is the LifeTime tool. And generally speaking, you can, expect it to be within a couple % of running HPOP on its own. And if you go look at the runtime, it is much faster to run the LifeTime tool. It's probably hundreds to thousands of times faster, depending on sort of what settings you have, whether you have a bunch of Gaussian quadratures turned on, the number of orbits per calc, that sort of thing. But the LifeTime typically is going to run a couple hundred to 1,000 times faster than running HPOP. So if you can get, 1,000 times faster and 3% of this exact same answer, that's what you might sort of expect when running the LifeTime, at least for most LEOs. One other thing, orbits per calculation. Pretty much this is how often you want to recalculate your orbit, and you can either do that once per orbit. You can do every 10 orbits, like update my drag value, things like that. Really, if you just increase this number, the orbits per calc, so in this case you're only going to sample every 20 orbits, it's going to have minimal impact on your prediction. Run roughly 20 times faster. The default is 10. If you just were to change this to 20 opposed to having it recalculate once per orbit. And you'll just sort of systematically see your LifeTime prediction will be slightly shorter if you decrease this value. The reason for that is if you sample the drag every 20 orbits versus every 1 orbit, you're just going to get a slightly more accurate updated drag value, which is going to tend to bring your satellite in a little bit quicker. Okay, so that is really the summary of all the general LifeTime settings. I've run a few more trade studies, particularly with GTOs. I'm not going to go into all the results here, but I am going to scroll down to one other interesting finding I found, which is what's being shown at the beginning of this video. And that has to do with orbits that decay sort of unexpectedly in my eyes. In this case, I ran a study that has pretty much random orbital elements with different satellite characteristics everywhere from LEO to GEO. And I ended up finding these orbits that decay, rather quickly, and I was really confused. So I sorted by radius of periapsis and their lifetime, and then I found that anything that happened to decay that had a radius of periapsis, I think, of greater than 10,000 kilometers, happened to fall into one of these two sort of inclination bins, centered around 63.4 and 116 degrees inclination, and there's probably a little bit of width there on the side, plus or minus about 10 degrees inclination or so. But it turns out that if you have a satellite at those critical inclinations, and those critical inclinations mean that the J2 effect of the Earth's orbit doesn't really twist your argument of perigee very much, so they will be sort of stable in their sort of orientation. It turns out that what can happen is the moon and sun can start pulling on your orbit in kind of the same way, and because your argument of perigee isn't being rotated due to the Earth's J2 effect in higher order terms, then it'll be, I guess relatively stable, and then the perturbations of the moon and sun are going to just keep on pulling on your orbit and change its shape. So it actually turns out if you have a radius of periapsis of 10,000 kilometers, it looks like, only a few of these orbits decayed. But as you increase, if you jump up to 40,000 for your radius of periapsis, which is about a GEO, it turns out almost 60% of them decayed in less than 100 years, at least according to the LifeTime tool. So I really wanted to check this, so I ran it in HPOP for the whole time, and here is one result. Down here is the number of years. This is pretty much an orbit that starts out in GEO, and you'll see it actually gets pulled and becomes this really elliptical orbit. The orbital energy is about staying the same, but you can see this sort of radius of periapsis value sort of fluctuate and eventually get pulled in due to these sun and moon effects. The LifeTime tool predicted, I think, a 37-year decay, which is actually this first orbital minimum. It actually didn't quite decay that first time, and it had this sort of weird bounce effect. But it's pretty cool to see that, this isn't just a fluke of the LifeTime tool or something like that. If you actually go and propagate these satellites, you can actually see this geo decay. So thanks for joining me. And if you want to run these trade studies on your own, you can go grab this code from our GitHub, our Analytical Graphics Inc. SDK code examples. It's located under Python, and you can find the LifeTime trade studies example there. Thanks, and thanks for watching.